Hey guys, welcome back to chapter 7. This is probably one of my most favorite topics to teach, so probably one of my most favorite videos to record. What we're going to do now is we're going to start mathing with these chemical reactions. So we're going to start to be able to predict what happens during the chemical reaction and predict how much we need to put in or how much we get out the other side. So the fancy name for this is called stoichiometry. So stoichiometry is the numerical relationship between the chemical quantities in a balanced equation. What stoichiometry is going to give us the ability to do is we'll be able to predict the amount of reactants needed to form a product. So if you think about working in an industry, it's probably pretty important that you can predict how much of the reactants that you'll need if you've got a shipment to fulfill. So let's say I'm making ammonia as my product. Probably need to know how much of the reactants to order in order to fulfill the 3 tons of ammonia that the customer ordered. So something really important to do. We'll be able to predict the amount of one reactant required to completely react with another. So again, let's use that example. What if we're making ammonia? So there's 2 chemicals that go into that process. If one's really, really expensive and the other one's dirt cheap, we probably need to know exactly how much of each one we need to order so that we can completely react all of the really expensive one. We don't want to leave any of that left over. And then it'll allow us to plan reactions with specific quantities. So if a customer orders 3 tons of ammonia, we want to plan it so that we don't make 20 tons and waste a whole bunch. So stoichiometry really is just the accounting in chemistry. It allows us to do a lot of really great predictions and account for the chemical reactions that we're doing. Before we dive into full-blown stoichiometry, let's look at a really silly example. So here's a recipe for pancakes, and this, I apologize, this is a really crappy recipe for pancakes. Don't try this recipe. I can't imagine that it tastes good, but we'll go with it. It's simple. So here's our recipe for pancakes. We have 1 cup of flour plus 2 eggs plus a half a teaspoon of baking powder. So we mix all 3 of those ingredients together, and that'll produce for us 5 pancakes. So what stoichiometry is really just a relationship between the ingredients. So it's this relationship that for every 2 eggs, I can make 5 pancakes. So let's say I go to my pantry. I have a whole bag of flour, so I have tons of flour. I have a whole box of baking powder, so tons of baking powder. I open up my fridge and I see 8 eggs inside of my fridge. What is the maximum number of pancakes that I can make? So I have 8 eggs. How many pancakes will that produce? Yeah, it'll produce 20 pancakes. So if you didn't see that right away, that's okay. I'm going to provide you kind of a systematic way to get to that. But if you look here, I took 2 eggs, and 8 is 4 times as many. So 2 times 4 gives me 8. So 5 times 4 is going to give me 20 pancakes. And that's all stoichiometry is. It's just that relationship between 2 things in our reaction. Okay. So let's do some different scenarios. So what if I open up my fridge, let's say I live on a farm, I got plenty of eggs, open up my fridge, I got tons of eggs in there. Open up my pantry, I've got a whole box of baking powder, but I look at the flour and I'm like, oh crap, I only have a half a cup of flour. What is the maximum number of pancakes I can make with a half a cup of flour? Yeah, I can make 2 or 2.5 pancakes, right? So I have half the amount of flour, I can make half the amount of pancakes. If you saw that and did that in your head, you just did stoichiometry in your head. It's awesome. Okay, so again, I got a whole bag of flour, still live on a farm, plenty of eggs. I open up my pantry and I have 1 teaspoon of baking powder. If I have 1 teaspoon of baking powder, how many eggs or how many pancakes can I produce? Yeah, I can produce 10 pancakes, right? Again, stoichiometry in your head. And now I've got a whole box of baking powder, still live on a farm, whole thing of eggs, and I've got 3 cups of flour. So I put those 3 cups of flour in, and how many pancakes come out? 15 pancakes. So you guys are doing stoichiometry in your head. The next slide is going to be molecules. And for some reason, when I go away from recipes into molecules, wires start to get crossed. But we're going to do the same thing here. So here's our recipe, and this is actually to make ammonia. But here's our recipe. Our recipe is 3 molecules of hydrogen, 1 molecule of nitrogen, and I get 2 pancakes or 2 molecules of ammonia out the other side. Okay. So what if I had plenty of hydrogen in my laboratories? I got a whole bottle of hydrogen, but I open up my cabinet and I only see 3 molecules of nitrogen. So a whole bunch of this, but only 3 molecules of nitrogen. How much ammonia could I make? Okay. Well, 3 molecules of nitrogen, 3 molecules of nitrogen would give me 3 times as many ammonia. So 3 times 2 would give me 6 molecules of ammonia. So stoichiometry in our head again. If I put the molecules up here and wires started to get crossed, that's okay. So the next slide is going to be the systematic way that we have to solve these types of problems. The other thing is, if you were to walk into a laboratory, we don't count individual molecules, do we? When we put something on the scale, what does that reading spit off? Yeah, it spits off grams, right? So we're going to have to add that into the mix somehow. So here is our map. Here is our systematic way of solving these problems. So right here, we're going to start with a certain number of eggs, let's say. So when we're in a laboratory, we typically measure not in number of eggs, we typically measure in grams. So this is going to be our grams of substance A, whatever we're starting with. But when we're doing math in chemistry, we don't do math in grams. What do we do math with? Yeah, we do math with moles. So the first step is going to be to go from grams of substance A to moles of substance A. And this step is actually a review of math that we've done before. If that is a little shaky, don't worry. I'm going to do a quick review of it. But you want to make sure that that's solidified because that is really just a review step there. Okay. The new step is actually this step down in gray. So now that we're in the unit of moles, we can use the moles of substance A to predict how many moles of substance B can be made or used. So how do we get from moles of eggs to moles of pancakes? We're going to use that balanced chemical equation. We're going to use the recipe. So we're going to use the ratio of coefficients. So I could probably add of coefficients in here. So ratio of coefficients from the balanced equation. And that's how we'll get from A to B. So 2 eggs, 5 pancakes. 1 cup of flour, 5 pancakes. That's the ratio there. Okay. And then in most cases, the unit of moles is kind of useless. So if I worked in an industry, my boss is going to say, how many moles of ammonia did you produce? He's going to say, how many grams of ammonia did you produce? So the last step would be going from moles of substance B back to grams of substance B. And again, just using the molar mass. I highly recommend that you have this roadmap or a roadmap that you write that works for you nearby when you practice these problems. So knowing where you are and what step you're going to is going to be really, really helpful when you start to do these problems. In my face-to-face classes, the students that recreate this map on their exams are typically the students that score the best on this exam because they have that roadmap to look at to see. Okay, so you guys can just simply place it next to you. You don't have to recreate it. All right, so it's time to practice. We're going to do this one nice and slow together. So let me read through this slide with you. So in photosynthesis, plants convert carbon dioxide and water to glucose. So glucose is this ridiculously big molecule right here. So here's the question. We want to know how many grams of glucose can be synthesized from 58.5 grams of carbon dioxide. So we're going to assume there's more than enough water, so we can ignore that. We haven't even mentioned oxygen, so that's not of interest to us, so we're going to ignore that as well. So what we're asking is we start with 58.5 grams of carbon dioxide. How many grams of glucose can we make? Okay. So the first thing I'm going to do is just recreate that map, but I'm going to do so in a way that is applicable to this problem. Okay. So according to the map, we start with grams of substance A. So in this case, we're going to start with grams. And what is our substance A? What is it giving us? It's giving us grams of carbon dioxide. So instead of writing a generic A, I can write grams of carbon dioxide. And then it gives me 58.5. Okay. What's the first step in our map? So I'm going to click back a couple here. So step one is going from grams of substance A to moles of substance A. Okay. So our map, grams of carbon dioxide to moles of carbon dioxide. And we're going to need the molar mass here to do that. All right. So that's step one. Oops, other way. Step two, so now we're in moles of carbon dioxide. So step two is the new steps. This is really the only new piece that we're learning right now, is to go to moles of substance A to moles of substance B. Well, what's substance B in this problem? Substance B is whatever it's asking for. So it's asking for glucose, or the C6H12O6. Okay. So let's click over. So moles of substance A to moles of substance B, and our substance B is C6H12O6. So that's step two, moles of A to moles of B, and we're going to use the equation to do that. Okay. And then the last step, is it asking us about moles of glucose? Well, of course not. Moles isn't very useful. It's asking about grams of glucose. So we'll have to take that last step and go to grams of glucose. And again, we're going to need molar mass. So there's our roadmap as it applies to this problem. So changing it from A and B to what is actually in our problem. Okay, so now we're going to do a series of unit conversions. So what's the very first thing we write down for every unit conversion that we've ever done, ever? The information that was given, the measurement that was taken. So 58.5 grams of CO2. And the first conversion that we're doing is a grams to moles conversion. So simple conversion here. So remember, we're going to let the units guide our problem. So whatever unit we're getting rid of, that's going to go on the bottom. So grams of CO2. And I'm going to tell you right now, it's really important that you guys start writing grams of what, or moles of what. It's going to keep your problems clean, clear, precise. Okay. All right, so we go to grams of CO2. That's what's getting canceled. What unit are we interested in? What's our destination? That goes on top. So moles of CO2. Okay. And we know we're going to have to use the molar mass. So in 1 mole of CO2, how many grams is that? So again, I'm going to, probably the last time I'm going to do this, but I'm going to explicitly do the molar mass over here on the side. So I go to the periodic table, I look up carbon, and I see it has a molar mass of 12.011. And in carbon dioxide, there's only one of them. And oxygen, I look at the periodic table, I see it has a molar mass of 15.999. And in carbon dioxide, there's 2 of them, so I'm going to multiply it by 2. And then I'm going to add those numbers together. So 12.011. Grab my calculator. All right, so 15.999 times 2. That's 31.998. And we add those together, plus 12.011. And carbon dioxide has a molar mass of 44.009 grams per mole. So 1 mole is 44.009. Okay. All right, multiply across the top, divide by the bottom. So 58.5 divided by 44.009 equals 1.33 moles of CO2. Okay, so that is step 1. That step hopefully should feel like or be a review step for you. Hopefully that was like, oh yeah, I remember how to do that. If not, go brush up on that quickly because you're going to need it. All right, so step 2 is the new step. Step 2 is going from moles of carbon dioxide to moles of glucose. So a mole to mole conversion here. Okay. So the first thing I'm going to do is I'm going to take my answer from the first step and I'm going to write it down here as a new problem. So 1.33 moles of CO2. Same thing here. I'm going to set up my train tracks. The unit that I'm getting rid of is going to go diagonal or on the bottom. So moles of CO2. So moles of CO2, moles of CO2. What's my destination in this step? My destination is moles of glucose. Okay. All right, so I know I used the equation here. So the numbers that go in front of mole here are going to be the coefficients from the balanced chemical equation. So it's a mole to mole ratio, if you will. Okay, so I'm going to click back to that equation. So I see carbon dioxide and I see glucose. What number, what coefficient is attached to carbon dioxide? The number 6 is attached to carbon dioxide. So that is going to stay with carbon dioxide. So 6 is going to go on the bottom there. Ooh, wrong way. What number, what coefficient is attached to glucose? Well, it's an implied 1, right? So the coefficient 1 is attached to glucose. So a 1 is going to go up there on the top. Okay. So mole to mole ratio, these numbers came from the balanced chemical equation. Multiply across the top, divide by the bottom. So 1.33 times 1 divided by 6 is going to give me 0.222. And what's my unit? Moles of glucose. Okay. That is the only new step in this problem. That's the only new thing that hopefully you should have to learn. Are we done? Well, of course not. It's not asking for moles of glucose. It's asking for grams of glucose. So we have to make this final step from moles to grams. So I'm going to click over to the next slide. So starting a new train track, I'm going to take my answer from the previous step. Start a new train track. And then get guided by my units. So moles of glucose are going to go on the bottom. What's my destination? What am I trying to figure out? Grams of glucose on the top. So moles cancel and we'll be left with grams of glucose. Again, this is just a moles to grams to moles conversion. We need the molar mass of glucose. So I look at the periodic table. I see that carbon has a molar mass of 12.011. And in glucose, there's 6 of them. I look at the periodic table and I see that hydrogen has a molar mass of 1.008. And in glucose, there's 12 of them. And then lastly, oxygen has a molar mass of 15.999. And in glucose, there are 6 of them. And then I'm going to add that together. So let me do some work here. 12.011 times 6. 1.008 times 12. And 15.999 times 6. Wah! There we go. Okay. Now I'm going to simply add those together. 72.066 plus 12.096 plus 95.994. And the molar mass for glucose is 180.156 grams per mole. So in other words, in 1 mole of glucose, there is 180.156 grams. Okay. So multiply across the top, divide by the bottom. So 0.222 times 180.156 tells me that 39.9 grams of glucose is formed. Okay. So if you work this problem alongside of me or ahead of me, you might have gotten something a little bit different than 39.9. You may have gotten 41. You may have gotten 38. That's fine. Please know that on the exams, of course, I go through and I hand check all your answers. But there's also like a 2% error window. So as long as your answer is within 2% of what I input, it'll automatically mark it right. And then, of course, I go through and hand check everything. So if it's close, I can always override that. So in this case, if it's close, that's good. That's what we're looking for. Okay. I've got one more problem in this slideshow. So here just kind of walks you through it. So what I suggest at this point, go ahead and pause the video. Try to work through this as far as you can. If you get stuck, then hit play on the video. I'll get you unstuck and then you move forward, pause it again and move forward. But go ahead and pause the video, try to work through this problem, and then I'll work it with you. All right, so one of the components of acid rain is nitric acid, and nitric acid is this HNO3, which forms when NO2 reacts with oxygen. Assuming that there's more than enough oxygen and water. So basically what that's saying is you can ignore water, you can nor oxygen. We're just focused on this guy and this guy. So assuming there's more than enough oxygen and water, how many grams of HNO3 forms from 1.5 times 10 to the third grams of the pollutant? Okay. So first thing I'm going to do, and I'm going to work through this problem a little bit faster because hopefully you guys have done it already and you're just kind of following along. So the first thing I'm going to do is I'm going to put together the map that applies to our problem. So we're starting with grams of NO2, and the first step is going to be moles of NO2, and that's going to be a molar mass conversion. Okay. Then we're going to go to moles of substance A to moles of substance B. So A in this case was NO2. B in this problem, what is it asking about? It's asking about HNO3. And then lastly, moles isn't terribly useful. We like the unit for grams. So we're going to go from moles back to the unit grams. So grams of HNO3 is our ultimate destination. Okay. All right. So now that we've got our map, let's start diving in. So series of unit conversions. The very first thing I'm going to do is write down the information that was given. So it tells me that 1.5 times 10 to the third grams of NO2 is present. Okay. So train track, let the units guide you. So the unit grams of NO2 goes on the bottom. So that can cancel. Our initial destination is moles of NO2 on the top. So in 1 mole of NO2, so I'm going to take oxygen 15.999 times 2 plus nitrogen 14.007. So this is going to be 46.005. Multiply across the top, divide by the bottom. So 1.5 times 10, 1.5 times 10 to the third, divided by 46.005, and I get 32.6 moles. Okay. Switch colors here just because we're going to a new step. All right, so that was step 1. Step 2 is our new step. So moles of A to moles of B. So this is the only new step that we have to learn. So I'm going to take my answer from the first step and start a new train track. All right, so let the units guide you. So moles of NO2 is going to go on the bottom because that's going to cancel. Our destination, or what we're interested in, is going to go on the top. So that's HNO3. And where in the world do we get the numbers to plug into this? Well, we got to go back to that chemical equation. Okay. So what coefficient is attached to NO2? The coefficient of 4. And what coefficient is attached to HNO3? Oh, also the coefficient 4. Okay. So multiply across the top, divide by the bottom. And what you'll see when you do that is that we also have 32.6 moles of HNO3. Okay. All right, so the last step is going to be going from moles of HNO3. The problem is asking about grams of HNO3. So we need to make that last step to grams of HNO3. Yeah. All right, so we're going to start with the information from the last step. So 32.6 moles of HNO3. Do my train tracks. Still going to let my units guide me. So moles of HNO3. And what unit are we interested in? Grams of HNO3. In 1 mole of HNO3, we've got 63.012 grams. Okay, so multiply across the top, divide by the bottom. So 32.6 times 63.012, and we get 2,054 grams of HNO3. Okay. Now that number does seem a bit high, right? So we haven't really dealt with numbers in the thousands before. But if you go click back to what number we started with a really big number, right? If I rewrite this, it's actually 1,500. So we started with a lot of grams of NO2. So it kind of makes sense that we should end with a lot of grams. So that's actually okay. So that's the end of this slideshow. The next topic is an application of this roadmap. So to solve the next problems, what we're going to do is we're actually going to do 2 cycles through this map. So we're going to cycle to substance B, and then we're going to cycle through to a substance C, and we're going to compare these 2 answers. So that being said, now is a great opportunity to stop and practice this skill. Make sure that you're fairly efficient, fairly comfortable with this skill before you go to the next video and before you add another layer on. So make sure this is clear, because we're going to get a little bit harder. We're going to apply this to another scenario. So I hope you guys found this helpful.